Once the spectral imaging data is collected, it's not enough just to have the elemental distributions. The analyst is usually interested in understanding what the compound, alloy, or mineral distributions are within the material. One way of doing that when you only have electron maps is to overlay the electron maps onto the electron image, the X-ray maps onto the electron image, and look for color changes in the overlays indicating where some of the compounds, alloys, or minerals may be. For a simple microstructure like the one in this example with only 4 elements, that may be easy and you might be able to find most of the phases that are available in the material. However, with very complex materials that may have upwards of 7 or 8 elemental maps present for the sample, it is much more difficult to have very high confidence that you will be detecting all of the compounds that are in the material. A preferred methodology of analyzing for compounds is to let a statistical program analyze all of the data set and find the chemically unique phases within the material. That is provided in NORAN System 7 with the COMPASS routine. COMPASS calculates the distribution of the different compounds in the material by comparing the spectral fingerprint or the spectral shape of every pixel compared to every other pixel spectral shape. If they are similar, they put them in maps together. If they are different, they go into separate maps. Then we will get a spatial distribution map and a spectrum associated with each of the compounds or alloys or minerals within the material and within the statistical significance. So anything that is chemically unique will show up as a unique map. So in this particular case, it's shown up as 4 different maps within the material. There's one additional interpretational tool that we have available, which is a phase analysis, which will take these COMPASS results and turn those into more interpretable, easier interpretable results with phase analysis. So if I press this auto button, that will turn it into a phase analysis. And that has summed essentially the first and the last maps into this map, and it has also provided us with a intelligent user-defined name on the compound that it is found. So in this particular case, it's determined that this is the nickel aluminum rich region. If we look down at the spectrum, we can see that that is the new nickel and aluminum rich particles that we had seen earlier in the point and shoot methodology. The globs are the yellow maps that is now classified as chromium cobalt because that is the spectrum that it best matched for the labeling purposes, and the spectrum that it shows has higher chromium and cobalt compositions in those spectra. It, in addition, found an extra component that we had not seen obviously earlier on, which is classified as the yttrium rich. If I click on that map and show, we can see that very clearly there is an yttrium peak in the spectrum with the nickel, cobalt, chromium, and aluminum, but there is now an yttrium-rich phase. And if we click on the legend for that phase, we can see that those are regions that are at the edges of the existing phases and also webs between the globular phases. So those are regions that we may not have seen visually in the electron image, may not have popped out at us as being quite obvious in the electron image, but statistically they are all similar compositions in all of these regions across the sample, and it has told us that this phase is available at all of these pixels within the field of view without us having to know that yttrium is a constituent in this actual material. So the COMPASS routine statistically analyzes the data set in a self-consistent manner for everyone that pushes the button, gets the same results, and it shows uniquely where all of these phases are across the whole sample.